I'd like to introduce myself. My name is Mitch Friedman. I'm an engineer. I've been in this engineering business for a long, long time. The things I do have primarily to do with scientists who need help in getting their work done quicker. Now, I was never involved in biology or medicine. When I was a young kid, I got out of college. I had 2 degrees. One from City College in general engineering, and had another degree from Columbia, where I specialized in fluid mechanics and optics and mechanisms. I was working at IBM in the early 60s, and I met a guy there who later became my partner. His name was Lou Kamensky. He's one of the smartest guys I ever met. Lou had the task of programming a technique of reading handwriting. Now, today, everybody can read handwriting. But at that time, the only way IBM was able to capture information from points of sales, other things, inventory, was you would fill out numbers very, very carefully in a little box. And it would always say, make the 8 like this and put it in a box. Some of you, who were born a while ago will know what an IBM card looks like. But if you don't, take my word for it. But anyway, it was really important for IBM not to be able just to read numbers and printed letters. They wanted to be able to read signatures. Now think about it. Today you scan a card or whatnot, they got everything. They didn't have it then. Now to have a person's signature at a point of sale and be able to sell that department store IBM equipment to read those sales slips was an amazing piece of business. So Lou figured out a way of scanning written signatures and plugging them into IBM system. It's a tremendous breakthrough for IBM. I didn't know a thing about programming. I didn't know a thing about scanning. I was designing machinery for IBM to make their tiniest little computer chips at a very high rate of speed. But everyone gets in touch with everybody else at IBM sooner or later, no matter how far you're spread out. And Lou was so well thought of by IBM, they made him what's called an IBM Fellow. Now, an IBM Fellow, it's not like getting the Nobel Prize, you understand, but what they did was they funded him with a laboratory, I guess for 2 or 3 years, and a technician to help him, and told him if he was going to pursue work in reading handwriting and the like, he can work in any allied field he wanted. IBM would pay for it. So Lou said fine, of course. And what he decided to do was very altruistic, I must tell you. He said if he could read somebody's signature, why can't he read a slide with blood samples on it? He can actually count the cells or decide what the biological material is on a slide. That would be a great breakthrough. So he tried to do that, and he failed. And the reason he failed, because you just can't read a slide with biological material by looking at it and counting little specks. First place, you can't see a thing unless you've applied different biological stains to the slide, which brings up the color. Different biological materials will take up certain stains. So if you were looking for a particular item on the slide, you'd have to know what stain to apply, and then you could scan the slide or look at it under a microscope, and then you could find that out. To complicate matters still further, the slide is not simple lines, a blood slide or a biological slide. It looks like the map of Europe. I mean, there's all kinds of crazy shapes. The demographics of that slide is impossible to deal with. Of course, now your cell phone could probably, figure that out. But at that time, the system that was in use by IBM was the System 360, then the System 370. The size of a desk would have 1/1000th the computing power of your cell phone. So Lou failed to do it by scanning, and he decided what he'd like to do, maybe he can take all these cells and he'll mix them with saline solution. I mentioned saline, all you scientists know why, because if it's not saline and it's water, it'll have a different pH, and it'll also have a different salinity, which means it's going to explode the cells. They have to be in the same environment where they came from. So he mixed them with saline solution, and I'm going to show you. He made this is like 50 times as high. He got somebody in IBM's lab to make him a glass block, and they put a groove in the glass block, And then he put a cover plate over the glass block, and then he had this little channel right there. And he began to pump the liquid and the cells through the channel, and he shined a focused arc lamp on top of the channel. And as this material was moving through, he wanted to count them. He did more than want to count them, because there's certain physics involved with shining lights and the interaction of light with material, which I'll go into later. But let's assume he just wanted to count them. Well, it worked pretty well. The only problem was, after he ran the patient's sample, he had to take the thing and clean it. It was like frying an egg and expecting the pan to be clean. It was like all this proteinaceous material had covered the inside of the thing, primarily from the heat of the arc lamp that he was using to illuminate it. So every time he had to run a test, he would set up for hours in order to run a 5-minute test. And they had this machine, this prototype that he built down at Sloan Kettering Memorial Hospital, working with people there. And it was a nightmare. They weren't getting any work done. And he read about what I was doing at IBM. I was handling particles 1,000 times bigger than cells, but nevertheless, he was interested, and we got to talk. And he told me his problem, which I understood. I said, Lou, I says, you can't make a machine to sell to anybody unless it works every single day. I mean, could you imagine selling somebody a telephone, and every time they made a call, they have to disassemble the telephone? He says, yeah, he's a problem, and so on and so forth. I says, what you really need, based upon what I see, is you need a pipe. Run those things through a pipe made out of water. He's looking at me like, what are you talking about, a pipe made out of water? You crazy? I says, no, a pipe made out of water. He says, how would you do it? And I said, let me think about it. What I did was I got this piece of thermometer tubing, piece of glass. Maybe it's about 1/4 of an inch in diameter. Okay. But the hole in that piece of glass, if you look at the end of it, is not this big. The hole in that piece of glass is this big. So that thing actually looks like this in cross section. And I took this piece of thermometer tubing, maybe 6 or 8 inches long. We put it into a glass blower's lathe, which is like any regular lathe, except both sides, it has chucks on both sides, and both sides turn at the same time. And I put a plug in one end. And in the other end, I put some air pressure in there, maybe 5 pounds of air. And at this point in the middle of the tube, I used the Bunsen burner, to apply a flame to this thing. And we started to melt the middle of this tube while pressure was on this end and the other end was sealed. Now what happens when you do that? When you do that, it's going to melt and a bubble forms in here. Now I've got this piece of glass tube with a bubble. Now since this tube is so small, this distortion of the bubble didn't really make much difference on the outside, but it did bulge it a tiny little bit. So here I had this finished piece of glass with a little bulge in it, and it had a hole through it with a bigger bulge in the middle. And then I took the thing and I cut it in half. And what did that give me? It gave me 2 pieces. One piece looked like this, and the other piece was just the opposite. So now I had this hole in the middle of the thing, which dimension-wise, let's talk metric, it was about 200 microns in diameter. Now blood cells are like 10, 12 microns, some are 8 microns, platelets even smaller, 2 microns. We weren't talking about platelets at that time, we were talking about cells. And I made this little piece of glass like this, and then I took this thing, I may have a picture of it already done. I took this piece of glass, this thing here, and I put a hypodermic needle in the middle of it, and I pumped the cells in through the hypodermic needle, And then I pumped saline solution around the outside. So we had saline solution coming in here. And we had the cells, I'll use a different color. We had the cells coming right in the middle. So here I have this little inner picture that looks dark blue. That's really crystal clear. You can't see any difference. What we did in order to take the picture of this thing, we put some yellow dye, actually we put some blue dye in the cell solution, and we photographed it through a blue filter, which makes it look black because we wanted to see it. Here you see nothing but saline solution coming around the outside. This is my bubble that I blew. And here are the cells coming up through the middle. And as they're moving up, the stream is getting skinnier and skinnier and skinnier. Okay? So now he had a, if you want to call it a flow cell, that wasn't going to clog because the walls were made out of water. It was constantly being washed. We left IBM to start a business because IBM didn't want to make these things. They said, we have more business than we can handle making computers. You want to make these machines and show them at IBM shows and show how computers can analyze the data. They said, well, that's great. But Lou didn't want to do that. I wasn't interested. I wasn't even interested in biology at all, to tell you the truth. Working for IBM was the best job I ever had as an engineer. I could buy any gadget I wanted, fool around with anything. They used to let my kids go to a circus every year. I mean, they had an IBM club. What more would an engineer want than that deal? But Lou comes back to me and he says, look, IBM doesn't want to make this thing, but they said whatever we did, they'll give us the rights to, as long as we mention IBM. I said, there's no way my wife's going to let me leave this job. You got to be kidding. He gives me a pile of books on cell biology and whatnot, which I never read in my life. I never took biology in college. I just took straight engineering courses. So I'm reading this stuff, and he's right. There are very few ways of counting and characterizing cellular materials and biological materials at high speed. So we started this company, and we had a great business plan, which in retrospect was the dumbest plan two engineers with degrees could have devised. What we said was, we want to make clinical instruments. We wanted to solve the world's health problems, or we wanted everybody to get their blood scanned quickly, you know, walk through something, you know, and you're done. But nobody at the FDA would let us put a machine like that in a hospital. No hospital would buy such a machine. It's a nightmare. It was still a nightmare back then. It's even a bigger nightmare today, but I don't worry about that today because I'm not in that business. But anyway, our plan, this great business plan, was we were going to make these machines and make them as flexible as possible and allow researchers to do research on these machines, because now they could count cells at a rapid rate. For example, if I ask somebody, how fast is that stream moving? How fast are those cells moving? If I tell them the first machine we built, the cells were moving at 20,000 per second, they couldn't believe it. The new flow cytometers out today, they go at 50,000 a second. So you can look at an awful lot of material, in a very short period of time. So here's our plan. We're going to make these machines. We're going to advertise it. Researchers are going to buy them or get a grant for it or whatever. And then when they write all these papers, we'll be famous. And then we just go to some big manufacturing company and we can sell these machines like hotcakes. Bad plan. All these researchers don't want to tell anybody what they're doing until they can go to some big show and write a paper or get it published in a world-renowned journal, which may take 5 years until they do all this research work, because these guys have two speeds, slow and reverse. We were going to run out of money. We had gotten some funding to start a little company, but you know, how long can that last? So we decided what we're going to do is we're going to let it be known that we'd like to do a deal with a big pharmaceutical company. So we went to what's called the Pittsburgh Conference. It's a famous conference. It's never held in Pittsburgh anymore. It used to be. But the one they're all over the United States. It's very well known. selling apparatus for scientists to do research work. So this was the Pittsburgh conference. At that time, it was in Atlantic City Convention Center. We set the machines up. We had 2 or 3 of them, and we were bombarded with questions. Every pharmaceutical company in the United States contacted us and wanted to know if we'd like to do a deal with them. We were overwhelmed. I never thought it would be that easy. And the companies that were most attractive to us was Becton Dickinson, Pfizer, Baxter Laboratories. Somebody, Baxter I think has been acquired by somebody else, Johnson & Johnson. And these guys came up and visited us in our small little lab and little factory in upstate New York. And we didn't know which guy to pick. And the deal would be, they would tell us what they wanted specification-wise. We would build the machines. We would sell at them a particular price, and they would do the marketing. We thought it was great. Who did we pick? We picked Johnson & Johnson. Why did we pick Johnson & Johnson? Now I can't figure out, but at that time, how could anyone find anything wrong with Johnson & Johnson? No tear shampoo, Band-Aids. I mean, how did we know? We didn't know that Johnson & Johnson also had 120 other companies with different names that were all part of the Johnson & Johnson company. So we made a deal with Johnson & Johnson, and we began making machines for these guys. Now, the first machines we made under our own name was called a cytograph and cytofluorograph. Some of you guys, and there's our picture again. We used that same shot. And we made one machine just to count cells. It was pretty simple. And then we made another machine, another version with different software to count and size the cells. Then we made another machine to count and differentiate using a fluorescence dye in the thing. And these are the machines that we were offering to the researchers, and we sold them. But then when Johnson & Johnson came on board, but then we asked them to specify a machine, and they specified it. We designed it, and this was what the first machine was, HEMAC, very original for hematology. And here again, this is our flow cell system, similar to that. And this time, we have a laser going through it. There the cells are coming down and going in single line right up the thing with flow of saline solution acting as the walls of the pipe. And this machine we made for maybe 3 years. We made them, we sold them, we made a great deal of money, and Johnson & Johnson sold it. But after a while, working for Johnson & Johnson became a problem for me and Lou. I don't want to go into the details. But when you sell your company, you sell your company. And you can't do what you really want to do. So ultimately, I left, and I started a small company called Union Scientific. And Lou started another company, and he worked at a lab at MIT. And we just left the company. Well, anyway, this was the machine that was sold by J&J for a while. It was called a HEMAC. Again, the very same flow system. And they were doing okay when we found out that they decided not to manufacture these machines, but they're going to license them to other people, which was probably a smart business decision on their part. And what they did was they gave a license to Becton Dickinson, they gave a license to Thermo Fisher Scientific, maybe 20 different people. They made more on the licensing than they would have made making and selling the machines. So anyway, I try to keep up with what they were doing, but ultimately, I'm not in the business. Then I happened to get this piece of literature after we left the company for this ortho, I don't know who assigns these fancy numbers, some marketing guru, I guess, hematology analyzer, blah, blah, blah. And I'm starting to read through the stuff. And all of a sudden I read here, it says, superior laser technology, counting and sizing by hydrodynamic focusing. What the hell is he talking about? He just got out of advertising school? There's no such thing as hydrodynamic focusing. And that's what really got me mad. And I said, one of these days, not only am I going to set the record straight, but I'm also going to tell scientists how this machine really works. So in case you're having a problem with it, you don't have to call the service guy like you do for your copier or your computer. You'll know how to diagnose it yourself. You'll be able to see in the results what is real and what has been papered over by some fancy electronics. So here's how it really works. There is no such thing as hydrodynamic focusing, okay? It's some advertising guy's idea of a catchy name to sell it. Now, the guys I really have to thank designing a flow cytometer is a fellow by the name of Bernoulli, who lived and did his work around 1738, a guy by the name of Pucelle, who worked in France and did his work in 1840, and a guy in America by the name of Reynolds. Now these guys were working in an area, for instance, Bernoulli, he was checking flow in pipes for one reason or another, and he was also checking how birds fly, how they get their lift, and he wrote a couple of equations. And Bernoulli says that total pressure at any point in a laminar flowing stream, if you got a stream, everything's moving without turbulence, in other words, not this, but everything's moving smoothly, then the pressure at any point in that moving stream, whether it's moving horizontal or vertical, is always going to be the same. Now what does that mean? What that means, here is that small diameter in that flow cell I just showed you, that little tiny diameter in there, and here are the cells moving along. Now, what he says, if I have a stream of liquid of whatever diameter is, and it's laminar, it means it's not bubbling around like what comes out if you force it, and it's laminar, that the pressure here has got to be the same as the pressure here, the pressure here, the pressure here. You say, how could that be? Well, what happens is the pressure is made up of two things. It's made up of static pressure, and it's made up of velocity pressure. When something moves fast, I'm not going to go into the calculus of it, when something moves fast, there's a component to the pressure depending on its velocity, and there's a component of pressure based on the weight and the amount of liquid behind it. Before I get into this for a second, let me go back to Pucelle. Pucelle was checking to see how blood flowed in people's capillaries. He really wanted to find it. Surgeons in France wanted to know, so on and so forth. And he calculated that the flow in a capillary, again, if it's laminar, this is the walls of our flow cell, is going to be in the shape of a parabola. The flow won't, but the velocity will. Now, any cells or any material or any liquid on the side of that capillary is moving at zero speed. It's not moving at all. It's on the wall, correct? The cells in the middle are moving the fastest. And by doing the calculus, it turns out that the average flow through this person's capillary, who he's doing for medical research, the average flow is equal to 1/2 the maximum flow, which he measured at the very center of the capillary. So we can use that to understand what's happening here. Here we have a bunch of cells. They're moving in the center stream. This is water out here. The water has nothing to do with changing the shape of this thing. That's what drove me crazy with this hydrodynamic focusing. This shape, parabolic flow shape, shows me that any cell in the middle is moving at the highest speed. The cells that are not in the middle are moving at a lower speed. But what's happening is, if this is higher than this, and this is higher than this, then the component of static pressure here is higher than the component of static pressure here, because the velocity pressure here is lower. So the static pressure is higher, and these two pressure components have to be equal. So if the pressure here is slower because the velocity, pressure here is higher, if the velocity is slower, it's going to push that little cell to the middle. And if there's cells on this side, same thing's going to happen. On the outside of the cell, that fluid is moving a little bit slower, and therefore there'll be more static pressure, which will pull the cells this way. And that is the centering model for the flow cytometer. That's why the cells wind up in the middle the way they do. And this other business of hydrodynamic focusing, which there are pictures of in all these advertisements that I've been reading about, that's total nonsense. Furthermore, our friend Mr. Reynolds, I'm going to set this down for a second. Our friend Mr. Reynolds, he came up with what we now call the Reynolds number, and he says that if I have a tube of material and it's flowing in laminar fashion, all the stuff is flowing like this. It's not flowing like this. If it's laminar, he can say certain things about that flow, and he can calculate the flow through the pipe and so on and so forth. Now, what he came up with, and we call it now a Reynolds number. He takes into account the velocity of the flow. It takes into account the diameter of the stream. It takes into account the density of the fluid, and it takes into account the viscosity. So if I have something that's very small in diameter, that component in his equation, this component of his equation of diameter is so small, it makes the Reynolds number so small, and once the liquid is below a certain diameter, the flow has to be laminar. This will never go turbulent because that thermometer hole is so small. There's no liquid on the face of the earth that can be pumped through a glass capillary and have it churn around. I don't know how many thousands of PSI you would need. I don't think it would go turbulent then. So now we have these three guys who lived hundreds of years ago, helped us to decide how flow through these flow channels really work. There's no focusing of anything. This wall is not focusing. This wall is made of this pipe is made out of water, and then there's an outer wall, and that bubble in there is just so you don't generate a whole bunch of turbulence. And that's how flow cytometer works fluid-wise. Now, I mentioned that I want to tell you how the flow cytometer works, but the flow cytometer is not only an instrument that's using fluids and fluid mechanics. It's using optics and it's using light. And basically, it's the interaction of light on matter, and you can find out how that light interacts with that matter. If you can measure it, then you can tell something about what you're shining the light on. Now, when something is moving, let's say it's a cell, something, and light is hitting it, a number of things are going to happen, whether it's in fluid or whether it's moving in the air or whatever. That light could either be reflected, that light could either be absorbed and come out much weaker. That light, possibly if it's transparent, could be refracted, in which case it might come out to the side. And then there's a third product of light and material, and that's called scatter. Now, scatter is a very, very sophisticated technique. It's not a technique, it's a process, and I cannot go through the calculus and the physics of that right now. But if you've ever looked at your window in the summer, with sunlight streaming through the window, and you see what looks like little shiny spots of dust floating around, those particles are so small you could never see them. If those particles were reflective and it reflected the light, you would never see them. But what happens is those particles act in a certain way, and I can give you some references on scattering, or you can call me. I'll give you my email address and my phone number, and we can talk about it. But scattering is a really important physical phenomenon. And what happens is when light scatters, light can scatter off of this particle in a forward way. Doesn't look anything like the reflected light. It could scatter in the back direction. It could scatter to the side. And this is called side scatter, forward scatter, back scatter. Now, by using a laser to impinge on this particular call it a cell, it's really not round, flowing in a stream of liquid. By measuring the scatter is more indicative of the size of the particle, which is an amazing thing. It's not just it's here or it isn't. It's here and how big is it? So by putting sensors, after you illuminate this with a light, you can see how big that particle is. So be able to do that at 20,000 a second is pretty good. It'll give you a distribution of the different kinds of cells and the different sizes. Here are these scatter patterns. They form in clusters. So we know there's that many cells in this size range, there's that many cells in this size range, because it's not a uniform distribution, biological material. It's a very valuable thing. Now, what happens is when you have a particle moving in this stream and it's being illuminated by a powerful light, that particle is over here, and as I told you before, because of these rules of laminar flow, all the particles in that stream, because they're moving in this parabolic fashion, are all going to be pretty much in the center of that stream. But as you measure smaller and smaller particles, it's possible that vibration in your laboratory is going to shake this little thing, and you want to make sure that a large cell that's moving fast gives a certain signal, but if you have a small cell that's moving really slow, it's going to be in the light a longer time. So you have a situation where you can have a tiny particle moving very slowly, which is going to generate just as big a signal as a large particle moving very quickly. And that's not good. It's going to screw up your results. And a lot of people who make these machines, they have forcing functions, they have all kinds of stuff. They can make something come out good, even if it's bad. So you really want to understand the physics of what's going on here. Now, it turns out, by a minor miracle, that a laser, which is used now, is a coherent light source. And if you look at the output of that light, it's going to be pretty much a perfect circle, but it's going to be very intense in the middle, and as I get out to the end, it's going to be less. So this is a graph of the intensity across that spot diameter. Now, this goes out forever if you had no constraints on the laser tube, but these 2 points here we call the E squared point. And that's the point at which there's virtually no energy left. Now think about this. I have cells moving in a tube, and I have a light source impinging on that little center. Now, if I pick my optics correctly, because I have this profile, okay, and it's called, by the way, it's called a Gaussian profile. Because I have that Gaussian profile, I can make it work for me. Because what happens is, if I refocus that laser so that it does this right across the flowing stream, think about this. Now I have less intensity here and more intensity here. And there are sensors measuring all this light scattering. So this cell, which is big, gets lit up by a very high level of intensity and sends out its signal. Now this other cell, which is pretty tiny, is out over here someplace because it didn't bother to follow, the parabolic profile exactly. That's going to be out here. It's moving slower than the one moving here. But it's moving slower, but it's moving through an area where the light is less intense. So you can actually write an equation for your optics and design it. So whether it's moving fast or slow, every cell gets light proportional to its size. That's basically how your flow cytometer works. And if you're getting strange results, look to that first. Your salesman's not going to be able to help you. the technician who services your machine may be able to help you based on hearsay that he heard from another company. But that's basically how that flow cytometer works. Finally, I hate to beat a dead horse with this hydrodynamic scheme focusing. I'm hung up on it. And it reminds me of a story that I heard. I don't know if it's true or it's been changed. But at the turn of the century, early 1900s, telephones were invented and were in common use. Also, wireless was invented. Ships at sea. All the heads of state in Europe had them at the turn of the century, 1900. And the Tsar of Russia is calling his ambassador in Paris from Moscow. And he's wondering about how does this wonderful thing work? So he talks to his science minister. He says, tell me, Boris. He says, how does this telephone work? I'm here in Moscow. My ambassador is sitting in his office in Paris, and I'm talking to him. He says, no problem, Your Excellency. He says, you should imagine a long dog whose tail is in Moscow and whose head is in Paris. You pull the dog's tail in Moscow and he barks in Paris. What could be simpler than that? The Tsar says, that's amazing, Boris. He says, but what about our ships out in the ocean? We're calling them, there's no wires out there. He says the same thing, Excellency, except you take away the dog. Now that is exactly the same as this hydrodynamic focusing. I hate to belabor it, but it got me so mad and was one of the reasons I decided to do this video. So the other thing I wanted to point out to you that after we did this thing, this is the very first patent on commercial flow cytometer. There's your glass tube. There are your scatter sensors. And we have maybe half a dozen other important patents, but this was the very first one. It was issued in December of 1972. There's my name on it, Mitch Friedman. There's my partner, Lou Kamensky, and we had another engineer by the name of Isaac Klinger who worked with us part of that time. And if you want to look up the patent number, you can. There are other patent numbers. There are cell sorters based on that same technology. Companies today do not publish manuals for how these things work. They really want to sell you reagents, particularly now that we have so many different fluorescent dyes. A fluorescent dye for a few grams of a fluorescent dye, you pay $400, $500, $700 for a little vial. It goes a long way, but that's how they make their money. So I wish you well. I hope your flow cytometers are giving you good, usable results and are helping mankind. But if you run into trouble, remember, the literature that you got from the manufacturer is less than helpful from what I read these days. Thank you very much.